Okay, so let's start. So last time we started with three-phase. So of course, three-phase is it AC or DC, by the way? AC. Definitely, it has to be AC. Okay, you can never have, of course, three-phase DC. All right. So AC, we saw actually there's something fundamental about AC, and you should know it already, which is the root mean square. Okay, the root mean square. So actually, before we start, let me ask you this question. So the question is, so first we have to know the definition of AC, right? You need to know the definition of what's an AC signal. Okay, so we have a signal that looks like this. And we have another signal that looks like this. This is, let's see.
Who is that one?
Yeah. I second that.
Okay. And we have a signal that looks like this.
It's technically the first two could be here.
Yeah, I was thinking.
Oh, no, 3 for 3.
All the equal. Yeah.
That's a Charlie Brown sweater right there.
Okay. And we have a signal that looks like this.
The answer is D, all of the above.
Okay, like it.
That one needs to get a sobriety test.
So which of these is AC? Which of these signals?
I'd say
3 of the 4.
3 of the 4. I don't know what that last one is.
Okay. So let's start with the first one. This one here, is it AC or not?
I would say yes.
It changes polarity.
What?
It changes polarity.
Okay, the first one is AC. The first one is AC. Okay. So what determines if something is AC or not?
Alternates current.
Okay, the main thing that determines if you have an AC signal or not is the average. Okay, the average of the signal.
The average should be 0.
All right. If the average is 0, that means it's AC. If the average is not 0, that means it's DC. Okay. If you have an average, actually the word average, another definition for it is DC. Sometimes they'll tell you what is the DC value of a signal. That means what's the average value of the signal. Okay. So the first one, because you know the average, if you take like there's a positive square, there's negative square, so the average is going to be 0. Okay. The second one is a sinusoidal wave, is also AC. Okay, so this is AC, this is AC. All right, so here I'm just right above them. So this here is AC. This one here is also AC. Okay. What about the third one?
Yes.
Yep.
The third one is also an AC because you see here there's a triangle, another triangle, and they cancel each other. So this is here is AC. What about this one here?
No.
Okay, this actually it's a distorted DC. Okay. It's DC. If you have an average, that means we are talking about a DC signal. Okay. So now the question is, since these are all AC, why is this the one that you actually see all the time? I mean, why they don't use this one? This one is easy, you know. If you want to know, I mean, this here, look at the difference, like mathematical. Like this one here, the sinusoidal signal. If you want to know what is the value here, you have to get a calculator and find the angle, then take the sign and find the angle, you know. But this one here, all you have to do is just look at it here, and if this is 10, for example, it's in, right? So why do they bother us and they always use this for AC signals and not use this easy one? Doesn't it sound easier? Does it look easier, right? A square wave is certainly easier to deal with, you know. then why do they always deal with a sinusoidal wave?
Imagine that's how it is.
Like, yeah, in the power, look at the power actually. If you like get an oscilloscope and you look at the signal that is coming, it will be sinusoidal wave. Okay? So why are they bothering themselves and bothering us and giving us the sinusoidal wave when there's an easier, shape? Okay, I'm going to tell you the answer. So the answer, because all the signals, there was actually there was a mathematician. His name was Fourier, who came up with this theory, and he says the simplest wave you can find is the sinusoid. Okay, all the other waves that you can see, they are actually a combination of sinusoids. All right, and in electromagnetism, here's the critical thing: in electromagnetism, only the sinusoid signal is the one that does the torque. Okay, so what happens is that when you push in a motor that signal over there, naturally what's going to happen? The square wave is going to break down into an infinite number of sinusoids. Okay, only one, this is called the fundamental frequency, only one sinusoid will be able to drive the motor. And what happens to the rest? What happens to the rest of the remaining sinusoids? They all go to generate hearing and pulsation. They're called harmonics. Okay, so only the fundamental frequency, only the fundamental sinusoid, the strongest one, is the one that will give you the torque, and the rest will generate harmonics. Right? So in other words, it's going to be inefficient. So to get rid of that, they will supply you always with sinusoidal waveform. Okay. So again, so all of these are AC, but it's really the sinusoidal waveform that is going to be beneficial to you. The rest, they're going to eventually they're going to break down into sinusoids. Okay, and only one of the sinusoids will be used to generate torque for you. The rest will be just hearing and vibrating. Okay. Is it clear? So in other words, electromagnetism naturally only works on sinusoidal waveforms. All right. You would try to push anything else, any other shape, you're just going to be wasting efficiency. Okay. So now the second thing. So we saw the definition of AC means something that has an average equals to 0. Okay. And we saw that always you're going to have a sinusoidal waveform, and the reason why is because otherwise it's going to be very inefficient. Okay. The third thing that is critical is to know the root mean square. Okay, so the average of the signal of the power signal is 0, but that doesn't mean it doesn't make power. Okay, all right. So the value of the signal that makes power is called the root mean square, the effective. In other words, if you touch it, you're going to feel that value. Okay? So let's take here an example. Okay, we have a sinusoidal waveform. Okay, and the peak value so the peak value over here, for example, is for example 200 and 270 volts. Okay, this is the peak. Of course, if the peak, if we're talking about an AC signal, that means the average is 0. That means the negative peak is going to be what? Negative 270. Okay. So the question is, what is going to be the root mean square, the RMS value? What is the RMS value? What? What is the voltage? What is the RMS voltage?
Is it 190?
Okay, so VRMS, what is it going to be equal to?
381?
It's going to be equal to 0.707 multiplied by the peak value. Okay, actually, you should know these already. All right, you should know these. So, what is going to be the RMS equal to?
190.85.
190. Okay, so 190.8. You said okay, 190.8.
How did you find that where it was those constants?
The 0.707.
Yeah.
Oh, there's a story behind it. It's really of mathematics, you know. You find the square root of the mean value of the square of the signal. Okay. In other words, really, you have to integrate, and you know, it's anyway for a sinusoid, it's always going to be 0.707.
It's the square root of 2 over 2.
Right? It's going to be 0.707. Right? So that's for sinusoids only for sinusoids. For a square wave, it's going to be actually equal to the value. So if you have a square wave like 10 volts, it's going to be equal to 10, right? But for a sinusoid, 0.707. So anyway, but you have to memorize it. You have to memorize it. What if we have, for example, what if actually let's have another example. But of course, I mean, you know, at the end, we're going to end up with 1 over square root of 2. I mean, after we do the calculation, we're going to end up with the, it's going to be equal to 1 divided by the square root of 2, which is 0.707. Okay? If that's what you're asking for. But the calculation for it is like it's mathematics, that's the integrate. Anyway, so let's have, for example, here. If you have if you have the following. Okay, if VRMS was equal to (120 volts), what is going to be the peak voltage? This is what you have in the electric power, right? In the US. So you have the root mean square delivered to you is 120 volts. What is the peak voltage?
169.7.
Okay, exactly. About 170. So you have, so that means the peak voltage. So V peak is equal to 170 volts. Okay. But which one do you feel? You feel the 120, not the peak. All right. So the effective value that you feel is 120 volts, even though the peaks can go to 170, you know, positive and 170 negative. Okay, so let's go back now to this here. So these are really like the fundamentals of, let's say, of AC signals. Okay. Now we're going to go one step further, which is three phase. Okay. So so again, so when you have so like I said, it comes naturally in electromagnetism. Okay, when you have a sinusoid, Sinusoidal waves are they come naturally in electromagnetism. Okay, when you have, for example, an electric field that's generated by a magnetic field and vice versa, they will always give you sinusoidal waves. So there's of course another thing which is frequency, but we talked about this before. Okay, how to find the frequency and phase, and Now, if you have in a three-phase system, you will have three power sources. Okay, three power sources. They have to be connected. The three power sources have to be connected such that the phase difference between the waves that are generated is 120 degrees from one to the other. Okay, 120 degrees. They cannot be in phase. They have to be 120 degrees out of phase. Okay, so you have, for example, here A and B and C. If you are going clockwise, A, B, C. Okay, sometimes they will number them, counterclockwise. A, B, C, counterclockwise. So here, for example, of course, each is 120 degrees out of phase with the other. Okay, each is 120 degrees out of phase with the other. So when you do that, when you put three voltage sources, 120 degrees out of, what about the frequency? What is going to be the frequency? Is it going to be, which will have the highest frequency? Which one will have the highest frequency? Definitely. They all will have, must have the same frequency, exactly the same. Okay? The frequency is important. It's critical to have the same frequency, or otherwise they can't see each other. Okay? If you have different frequencies, they will not be able to see each other. They will just pass through each other, and one of them will be used to generate torque, the other will be just harmonic. Okay? No, actually, the other will just be causing heating and vibration. Okay? So, so it's important actually to remember that. Always, the lowest frequency one is the one that will, do the torque. The one with the lowest frequency. If you have, different frequency sources, right? But here in three-phase, remember, you must have the same frequency on all of them. This is a critical thing. Okay? But of course, they will be out of phase with each other. So when you have a three-phase connection, in the 1980s, actually, they decided to have multi-phase. They actually, we will see sometimes, rarely you will encounter like, systems or books that talk about multi-phase. They had that in the 1980s and they stopped it. They never, they never actually went back to it. So three-phase systems, there's two connections. There's two different connections when you connect three-phase systems. Okay. Now you have to remember something. These three-phase systems, they are typically going to be secondary windings of a transformer. Okay, or of a three-phase generator. They're the windings of a three-phase generator. So that's why they will draw them as windings, as you see here. Okay. Because, like I said, they're either secondaries of a transformer or they're coming from the windings of a generator. So they can be connected in two different ways. You have the Y connection, like you see here. Why is it called Y? Because it looks like the letter Y. Okay. Another name for it is a star. The star or the Y connection. And there's a delta. Okay, there's a delta connection. So let's see the difference between the two. So these are the most common two. Well, there are only two connections possible, and let's look at differences between them. So when you have a Y connection, of course, the Y, if you look at it, it has an advantage over delta in one thing. How many terminals can the Y have? Look at it carefully. How many terminals can it have? It will have 4. Okay, so you can have A, B, and C, and you can have the neutral. Okay, the neutral terminal. The neutral terminal typically will connect to the ground. Okay, but not always, but it will typically connect to ground. The neutral will carry, the usually, I mean, zero, after, passes through all the three, So it will be, that's why it depends to the ground. So in other words, it can be grounded. Okay, the network can be grounded. The delta, on the other hand, you only have three terminals for it. You have A, B, and C. Okay, we're going to see the differences between the delta and the Y. So something to remember, or actually let's say to define. So when you take any two lines, this is called the line-to-line voltage. Okay, so if they tell you what's the line voltage, that means you are talking about the line-to-line. You take any two lines of the three, and you measure the voltage between them. Typically, this is the one that you have access to. Okay, this is the one that you always are going to measure. Okay, not the phase voltage. We're going to see the phase voltage in a minute. Here in the delta, the phase is the same as the line. Okay, why is that? Because when you measure between A and B, for example, you're measuring between two lines, right? So it's line-to-line voltage. But at the same time, you are measuring between the two terminals of the phase A. Okay, of the power source A. All right. So that's why for delta, the line-to-line corresponds to the phase voltage. Okay. So phase voltage is the amount of voltage as measured across an individual phase winding. So in other words, if you measure, let's look at this voltmeter here. Okay, this voltmeter here will have the same reading as if you are measuring between A and B. Okay, like for example, here we have, for instance, between A and C is measuring. This is the line-to-line voltage between A and C, but it's also measuring the phase voltage for winding C. Okay, do you see that? Do you see that? This here between A and C, you're also measuring, this phase winding. Okay. So now the line current is different from the phase current for a delta. Okay. So the phase current means the current that is passing through the phase. So in other words, to measure the phase current, you have to place the ammeter over here. Okay. But the ammeter over here is measuring what? What is the ammeter measuring here? It's measuring the line current. Okay, it's measuring the line current. The line current over here is equal to the phase current C plus the phase current B. They both meet over here at this point, then they move together through the ammeter. Okay. I think we should take an example. We're going to take an example in a minute, but let me just show you everything, the differences. Now, for a Y, the story is different. The story is different for a Y. Okay. In a Y connection, the line current is equal to the phase current. Why? Because you have here the phase. The current passing through here is going to be the same as the current passing through this line. Okay. So line current is equal to the phase current for a Y. But the phase voltage is not equal to the phase to the line voltage. Okay. Let me just write this summary over here. This is very important. So for a Y connection, a Y connected three-phase system, here's a summary. A Y connected I line is equal to I phase. Okay. All right. The line current is equal to the phase current. All right. The here is really a summary of everything that we're going to see. Okay, the phase voltage, or let's say the line voltage, is equal to 1.732 multiplied by the phase voltage. And where did the number 1.732 come from? Anyone know? Okay, this is the square root of 3. Okay, this is the square root of 3. All right. Now for the delta connected,
It says 3 over the square root of 3.
what?
1.732.
The square root of 3.
Oh, it's just the square.
Okay.
Oh, yeah.
So for a delta connected network, I line is equal to 1.732 I phase. Okay. And V line is equal to V phase. This is it. This is really a summary of everything in this chapter. Okay. Okay. So for a Y-connected network, the line current is equal to the phase current. And why is that? Because you saw here again. So let me just here. Let's look at it again. As you see, this is the phase. This is the phase voltage. This is the power source. One of the windings. Okay. The current that passes through this winding is the same as the current passing through the line, right? Do you see that? And that's why I line is equal to I phase. All right. But the voltage from line to line over here has two voltage sources on it. There's this one here and there's this one here. Now, are they connected in series or not? Are these two windings connected in series? This winding and this winding? Then how are they connected? In parallel? Between this terminal and this terminal, how are these windings connected?
I guess it is series because the loads are.
Okay, actually they are not. They're not connected in series, they're not connected in parallel. Okay?
Correct.
If you have a connection in between, that's not, they're no more in series. Okay, be careful. So they are not connected, they're just connected. But they're not in series, they're not in parallel. Okay? They are just connected. Anyway, the value here, the voltage is gonna be 1.732 multiplied by the V phase. Okay, the phasor voltage. Okay, so this is for the Y. For the delta, we saw that the phase winding is actually across two terminals, right? So that means the phase voltage is going to be equal to the phase to the line voltage for a delta. Okay, but the current is going to be bigger than the phase current. So the line current is going to be 1.732 multiplied by the phase current. Okay, you need to memorize this, right? This needs to be memorized. So really, that's it. This is everything for this, now let's do some exercise. So I'm going to give you some exercise now, just so that you understand these. Let's do this example here. Okay. So we have the line phase voltage in a Y-connected system are different. The voltage measured across the phase winding will be. Okay, so no, that is not worth it. Okay, so here let's do this example here. So what is going to be So here we have a three-phase Y-connected system, 120 volts per phase. Okay. What is going to be the voltage between, for example, between this terminal over here and this terminal over here? You measure the voltage. You take a voltmeter and you connect it between these two terminals. What is going to be your reading?
207.84.
Exactly, 208 volts. Remember, this is what you measured in the lab, 208 volts. Okay. If you take the measurements between any two lines in a Y-connected system, you're going to measure 1.732 multiplied by 120. Okay. And we saw for the Y connected is going to be V phase going to be equal to V line, but it's going to be the current that is going to be different. Okay. So what example? Okay. So let's look at this example here. This is the power source. Okay. It's like I said, it's the secondary of a transformer, or it's you know, coming from the windings of a three-phase generator. Okay. Now here's the assumptions that must be done in order to proceed with this with you know, with this example. So for the first thing is we have a pure resistive load. Okay, a pure resistive load. Now this is important because if it's not pure resistive, the numbers you're gonna get are not gonna be correct. Okay, that's why you see here it's a pure resistive load. Now the question is this common? Is it common to find pure resistive loads or not? What do you think? Are the loads usually gonna be pure resistive or not?
No.
Okay, why?
Just imagine it'd be really hard to have a pure resistor.
Okay, the truth is, usually, or actually almost never, you will encounter pure resistive loads. Okay, most of the loads are going to be highly inductive. Okay, highly inductive loads. Why? Because really everything includes coils. You know, everything, whether the motors or transformers or, you know, everything has coils in it. The coil is an inductor. Okay. So actually, you encounter mostly highly inductive loads. It's going to be a combination, of course, of both resistive and inductive. But the inductance is going to be considerably high. Okay, it cannot be ignored. But here, just for you to understand how three-phase systems work, we're going to assume that you're only going to encounter a pure resistive load because if you have inductive load, the calculations are going to be significantly different. Okay, it's going to be significantly different, and there's going to be, of course, phase. It's going to introduce, you know, it's going to phase shifting, and the power factor is going to be different, and a lot of things. Okay. So we're going to just encounter here a pure resistive load. All right. If you want to understand more about this, then you have to actually take another course. Let's say usually it's going to be electrical circuits level 2. You know, where you will spend your time just talking about inductive and capacitive loads. Capacitive loads, really, you will never encounter it. The only place you'll encounter capacitive loads is in microelectronics. Okay. Otherwise, capacitive loads almost never exist in a manufacturing industrial setting. Okay. So the first thing is a pure resistive load. Number 2, we're going to assume the load is balanced. Okay, and this is also critical. A balanced load means you see here it says 4 ohms. It means Z per phase. Okay, the impedance per phase is 4 ohms. In other words, it's 4 ohms is going to be over here, and 4 ohms over here, and 4 ohms over there. Okay, all of these, each one of them is 4 ohms. Okay. Now, is this a case that you encounter? Usually, yeah. Usually, if you have a single load, it's going to be balanced. Okay, whether it's a motor or, you know, it's going to be a balanced load. Okay. But if you are powering a system, a big system that includes multiple motors and multiple loads, then it's a different situation. Okay. So now let's proceed. Who can tell us? Okay, so we have here E, that's voltage, you know, E per phase, the phase voltage on the power side, the generator side, the current per phase on the generator side, the line voltage on the generator side, the line current on the generator side, and then we have the same for quantities on the load side. Okay, you have all the information you need. Who can tell us? One of these quantities? So there's 7 quantities that we're looking for: 4 over here and 3 over here. Who can tell us one of these quantities? I'll tell you what. I'm gonna make it even more interesting for you. Please find the power also. The power on this side, and the power generated and the power consumed. Okay, you seems like Guido. Can you tell us anyone of them?
Picked the wrong one.
Okay, who can tell us any one of them?
Say the phase voltage is 208.
What is that?
The phase or
Phase voltage is 120 volts.
there you go.
Good. The phase voltage on the generator over here
Yes.
Okay. is 120 volts. Good. So why? Because we have here. Are you with us, Taylor?
Yes, I'm with you.
Okay. So we have here 120 volts. We have 120 volts, the phase voltage. Good. What another quantity can you find? What another quantity can we find? Okay, really the easiest way is to first start with the voltages. Okay, then the currents. Now we determined the phase and the line voltage on the generator side. Obviously, on the load side, the line voltage is going to be equal to the line voltage on the generator, right? Because I mean, if you measure from here between this point and this point, it's the same as if you're measuring between this point and that point, right? It's the same thing. So what is going to be EL here equal to? 208 volts. Okay.
So the other one's 120.
Exactly. So that means since the load is also connected in Y, the E phase here is going to be equal to 120. Okay. All right. So the first thing we found is 208 on the line voltage, and 120 volts on the phase voltage. Okay. All right. So what is going to be the next thing that you can find?
Phase current.
How do you find
We
it?
have a resistor. Well, resistance.
Okay.
So it'd be.
Just apply Ohm's law, right? Ohm's law. You have the phase voltage between this point and this point and the neutral is 120 volts, right? And you have the resistance is 4 ohms. So what is going to be the current?
30.
Is going to be 30 amps. So it's going to be 120 divided by 4, and that will give you 30 amps. Okay, that will give you 30 amps. So what is going to be? So what is going to be the line current? You have here a Y connected network, right? You have a Y network, and we said what is the rule for I line equals to what? Is equal to I phase. So for a Y connected network, I line is equal to I phase. So that means the line current is going to be equal to 30 amps as well. All right. Now, obviously, since it's the same line that is going from here, and it doesn't branch anywhere. It goes to the, connects directly to the line current coming from the generator. So that means I line is going to be equal to I line on the generator side, right? And since the generator is connected in Y, that means I line is equal to I phase on the generator. Okay. And of course, it's going to be 120 volts. So we are done. So we have found all the quantities that we need. All right. Now the question is, what is the power? What is the power equal to? Okay, so the power, is equal to, this is a pure resistive load. Okay, it's pure resistive load, so that means that the kVAs are going to be equal to the kilowatts. Okay, so the power, remember, is equal to I multiplied by V per phase. Okay, the power per phase is I multiplied by V. How many phases do we have? There's 3. So you multiply 3 by I by V. Of course, I phase, V phase, multiplied by 3. Okay. And the power on the the power on the generator side has to be equal to the power on the load side. If you do I phase multiplied by V phase times 3 on the generator and the same thing on the load, they're going to be equal to each other. Okay. Why is that? Because the power drawn is equal to the power consumed. You cannot. There's no power that can be created or destroyed, right? Okay, let's take another example. Any questions so far? Any questions?
The power then would be 120 times 30 times 3.
Exactly. Yeah. Okay. All right, let's take another example. Over here. Okay, I'll give you some time to do this question. And then we'll do it together. Okay, so who can tell us, for example, what is the easiest thing to find? What is the easiest thing to find in the 7 quantities over here?
The V phase.
Okay, and what is E phase on the generator side? What is it going to be?
480.
400. Do you guys agree with him?
Should be 277,
Oh,
277.
sorry.
Okay, so here we have a Y connection. Okay, so the phase value is going to be lower than the line value. Okay, because the line you see how many there's in between. There's 2. Okay, so the line voltage is going to be larger for a Y than the phase voltage, right? So the phase voltage is going to be 480 divided by 1.732. That's going to give you 277, right? But there's an easier quantity to find. What is the easier quantity to find? Andrew? The amps? Are you sure? Okay, who can tell us what is the easier quantity to find than E phase over here? Without doing any calculations, you can find that quantity. What is it?
The V line equals V phase.
The what?
According to this in delta, V line equals V phase, which was what I was saying earlier.
Okay, so over here, which one of these do you find is the easiest to find?
Either is the same.
What?
They'd be the same.
480.
Okay, yeah. So the line voltage on the load, right? The line voltage on the load is going to be equal to the line voltage on the generator, right? So this is going to be equal to 480. So this here is 480. Okay, what is the next easiest thing to find? Let's see, I'm sorry, Ross.
The phase voltage,
The what?
phase voltage on the load.
You mean on the load? And what is it going to be equal to?
480.
Exactly. So this one here, the phase voltage is going to be equal to 480. Why? Because you have delta connected load. Okay. All right. So we have found E line. We have found E line on the load. We have found E phase on the generator, and we have found E phase on the load. What is the easiest quantity to find after that?
The line current for the load,
No. Before that.
phase current for the load.
Okay. And what is it going to be equal to?
Would be 80 amps.
Okay, so we have 480 is the phase voltage, right? And we have 6 ohms is the phase resistance. So what is going to be the phase current? 480 divided by 6. What is that going to be equal to? 80. amps. So we have here. Okay, we have 80 amps. All right. And then, what is the next easiest quantity to find?
The load and phase current for the Y connection,
The what?
the current for the phase and the line on the.
How? The phase current on the Y. How do you find it? He says the next easiest quantity to find is the phase current on the Y. And the question is, then show us how do you find it?
Well, no, I guess it'd be the line current
Huh?
for the delta.
Okay, good. So the easiest thing now to find is this, the line current for the delta. Why? How much is it going to be equal to?
138 point.
It's going to be 1.732 multiplied by 80. What is that going to give you?
138.5.
Exactly. Okay. Okay, now it's straightforward, right? What is going to be the next quantity to find? Andrew,
Which one?
what do you do next?
The
Without looking at the notes, look at the board, please.
phase primary.
Look at the board. What do you think is going to be the next to find?
The I2 or the IL.
Okay. So the line current here is the same as the line current there, right? It's the same thing. So what is it going to be equal here?
It's gonna be same.
Exactly. Okay. Finally, what is going to be the phase current?
The phase current,
Huh?
you just divide the 480 divided.
Are you sure? For a Y, what is it going to be? It's going to be the same. Okay. It's going to be the same. All right. So, in other words, you need to really the only thing you need to remember is this. Okay. Really, this is the rule that you need to remember for a Y and for a delta. Okay. So there's a homework. I'll tell you what. Try to review the lecture today, and I'm going to put a homework. But I think there's a homework over here. Now we're going to look at this later, but let me see. So there's the homework. But I'll tell you what. Just review, and the next Monday we're going to go over this homework. Okay. All right. Any questions?
Could you go back to the other picture? To the painting? No,
Okay.
not this, the other, on the paint tab.
Oh. All right, really, these are the rules that you need to, if you know these rules, remember them, you understand them, really, that's everything you need. Everything will be easy, okay? Okay, so I think we can stop at this point. And we'll finish next class.